So good morning, I was saying. Okay, so Scoop asked me if I could possibly do a seminar, and this is my attempt at doing what casual discussion about diffuse lighting. Casual. What do I mean casual? I made a talk at Revision 2020, so 2 years ago. Have you guys seen it? No, you.
No.
Okay, you've seen
I'm
it.
sorry, I didn't see it. Oh no, I guess I've seen it actually.
You've seen it. Okay.
I've heard some things.
Okay, so yeah, the thing is, when I did this seminar, there was way too much stuff to cover. I think I've covered like maybe half what I had in mind at the time, and the other half was not, well, first I didn't have time, and it was not ready in any case or shape. And ever since I've been like, it's been in the back of my mind, to try to cover those stuff, and but it's not ready. So I have like this long burn thing that I'm preparing, which is absolutely not ready. In particular, I'm trying to find, like a sort of a story, like something that gets you from a point to another point to another point to another point. So I can like like get the audience and get them through the different thing you want to talk about in a very logical way. And I still have holes in that line. Like, and every time I look at a place where I'm like, okay, how do I go from here to here? And then I discover there is this world of stuff that I realize that I don't know, and I have to study it. And so I have bits and pieces that are ready, but mostly it's not finished. One of the aspects that I didn't talk last time and that I plan to talk about is diffuse lighting. So diffuse lighting is basically who is familiar with rendering? Who is not familiar with rendering at all? Like, who doesn't know what I'm talking about when I say diffuse? You all know what diffuse is. Okay, cool. So yeah, diffuse is one thing that I want to talk about because it's such a difficult topic, but also super interesting. Usually the way I work is I prepare my slide in advance and I try to polish them and I try to have something like really nice with the diagrams and everything. This is not going to be the case today. Today is going to be a little bit of a mess. When I say I have something like that I'm preparing in the back, like it looks like that, it's going a little bit out of hands. Yeah, I hope so. This is mostly unprepared, but I hope that the work I've done like before is going to still make it interesting. Also, since we're in a small committee, I mean, it's super nice to finally be at a demo party with people, like not talking to my web camera. So because it's casual, because we're face to face, don't hesitate to interrupt me if you have like any question. If there is something that you don't even know what I'm talking about, like we stop and we like make a huge parenthesis, and that will be totally fine. So today we're going to talk about diffuse. So a little bit of history. 1760, we have this guy, Johannes Lambert. He publishes a small book, well, like a small essay, Photometry. And he does a couple of things in this. First, he invents the word photometry, like that's where the word comes from. Like, this guy has the idea that we could measure light somehow. So, photometry. I'm not a linguist, but I guess you can see where this is coming from. He determines experimentally a couple of laws of light. The fact that if you have a source of light and you have a wall and you put the wall like farther and farther from the source of light, you have like the inverse square law. Talks to everyone. Another law that he establishes is the cosine law. So if you have like a directional light and a plane, depending on how the light is oriented to that plane, the intensity you have follows a cosinus law. So he does that, and that's pretty cool. The cosine law is quite easy to figure mentally. So you imagine like you have a beam of light that arrives on a plane like this, and depending on the angle of incidence, you have like this. The beam of light is going to spread on a different surface, like if it arrives like straight on, or if it arrives at an angle, you have like a different area of that is lighted, but you still have the same energy that is arriving. So per unit, you have less energy if it's how is it at a grazing angle. So we have A, we have B, we have an angle, and we have a cosine relationship between the two, and that's what Lambert found and published in his book in 1760. So yeah, this is the law that we have. So that's something that's high school level math, I guess. And this is like probably the oldest lighting model that exists. I think that's the first lighting model. So he showed that the apparent brightness of something that you light up is going to be proportional to the cosine of the incident angle, and that's what we now call the Lambert cosine law. So I said that he also demonstrated how intensity relates to distance. And when I say demonstrated, I mean that he verified that, like a scientific approach, making experiments, like putting a model and then like verifying it. And verify that the law you write correspond to what you observe. So now, something funny is you have to imagine that he did that 240 years ago. Like at that time, this is what the world was looking like. I mean, so here's a pop quiz question. Like, how do you do that? How do you measure, like, how do you prove a law about light intensity when there is no device to measure light intensity? Like, the device is not to be invented until 1893. Like, even the light, like an electric bulb, is not to be invented for 40 years.
I guess you use the sunlight. Probably the only light source you have which is consistent and not flickering all the time.
That is not the source of light that he used. He actually used candles. So,
oh God.
So you have to imagine, like, the guy like establishes the inverse square law, establishes the cosine law, and you have no equipment to measure the light. Like, how do you do that? I guess the answer is by being like a pretty clever guy. So this is one of the experiments that he did. So this is the inverse square law experiment. So you have like one candle on one side, two candles on the other side. You estimate that the two candles are probably going to be twice as bright as one candle. And you have a wall in the middle. And then you try to make the lightness, like the brightness of the two sides match. And you see at which distance it matches, which is pretty clever, I guess.
Brilliant.
Yes, right. And I don't have the illustration for the cosine law, but I guess it's something quite similar. So the Demoscene being an aging population, I think this could be like quite a funny scientific experiment to do with your kids if you have any. I mean, you have to stop and give the guy some credit and be like, okay, that was really clever.
Teaching shader coding by using candles.
Yeah, exactly. Anyway, so in the last episode, we looked at what happens to, so you've seen it, you haven't. We looked at what happens when rays hit a surface. So some of them, they get reflected, some of, like the others, they get refracted into the material. And we saw that depending on the geometry that you have, like when you look at with a microscope, the rays that are reflected, they can go like in a spread in different directions. Even though the surface might look super flat like, I mean, this table looks flat to me, but if I look at with a microscope, it's not. What else did we see? We saw so the more geometry you have, like the more it's going to spread out, and the less geometry you have, the more it's going to come to behave like a microscope. This property of the surface, like whether it spreads or not the rays, we call that the roughness. And the contribution of those reflected rays, we call that the specular component in the model. Okay, I'm not going to risk it. This is still a part that I'm working on, like who invented this model. I think it's Torrance and Sparrow, but I'm not 100% sure. So we saw that we could represent like how much light. Is it slide? Okay, this slide is working correctly. We saw that we could represent how much light coming from like a given incoming direction is reflected to a given outgoing direction can be represented with a distribution function, which we call a BRDF. So the bidirectional reflectance distribution function. I'm not going to talk about this, just reminding that this is what we talked about last time. If you have questions during the talk, feel free to interrupt me again, no problem. And we saw one popular BRDF, which is for the specular reflection, so the one we talked about, which is the Cook-Torrance model. So a quick explanation about this guy. So there are three functions over here. So we have the normal distribution function, which says like how much the faces, when you look with the microscope, like they are completely off or whether they are aligned or not. So this is what this function does. And basically what this function says is, okay, what is the proportion of facets that are oriented so that they reflect? You know, we know the Snell law with the mirror that says if you have a ray coming here and it's going to go there. So the question is how many of those faces are aligned so they would do that. So that's what this function does. Then we have the geometry function, which says, okay, like if you imagine you look with a microscope and it looks like mountains. So how many rays are going to be occluded? Like how many faces are not going to receive light or reflect light? And then we have the Fresnel function, which says, okay, how many rays are going to be reflected as opposed to getting absorbed into the material. And you multiply all of that together, and that tells you how much light you're going to see from a macroscopic scale. The n.v and the n.l, they account for how big the microfacet look, seen both from the light direction and from the viewer's direction. The 4 comes from the derivation. I'm absolutely unable to show you how, but like basically when you put all the equations together and you derive, you get this 4 that pops out. So this is where it comes from. Yeah, I'm going to mention it again, but this derivation is mentioned in a pretty cool GDC talk. So I'll come back to this later. Anyway, so we saw that the light that are refracted in the material, they may scatter because the material is usually not homogeneous. So you know you have like your little ray that's going through, I don't know, maybe some glass, and then it hits some quartz, so it changes direction. Then it hits something else, it changes direction, and the when it goes through the material, it also might get tinted. You know, like you lose energy. So you had white light at the beginning, but then you have more and more frequency that disappears. So your wave is going to change color as it goes through the material. And so the idea is you have those rays that come into the material, they bounce in every direction, they lose energy, and then they come out pretty much in random direction with a different color. And that's what we call the diffuse component, and that's what makes this chair black, for example. Black is not a good example. That's what makes this couch orange. I mean, it works, but you know, as an example, it's not a good example.
I mean, the chair is mostly using spectral highlights anyways.
Yeah, that too. And actually, I saw like a very cool paper that was arguing that the thin layer is like playing a huge role in the appearance of a leather chair like that. You know, like you have if you look with a microscope your chair, you have actually like a thin layer of grease or something like that on top of the leather, which is going to cause some interference in the light that bounces off. So when you have like, for example, a white light, it's going to spread a little bit, you know, like do those rainbow things that you can't really see. Like I don't see a rainbow on this chair. But if you model this on a computer and you do one with or without this interference, it really changes dramatically the, well, dramatically is a big word, but you know, like we graphics people. But yeah, it's going to look boring if you don't have that. So funny stuff. Anyway, the one thing is, if you're far enough and you see those, so those rays, like they travel a little bit in the material, then they get out. But from a human scale, if they get out at a point that you can't tell apart with your puny eyes, it looks like it's coming from the point where they entered. So this light that comes out from the point where it entered, that's what we call diffuse component. And if it travels a little bit and go farther, for example, this bottle, it's the same effect, but we see the distance. We see like, well, this is coming from a different point where it entered. It's the same effect, just different scale, and then we tend to call that scattering, but it's the same thing. So this effect, the diffuse, I didn't talk about it. So we're going to try to see a little bit of that now. And we're going to start with the simplest form, which is the, and also the most intuitive, which is Lambert, which we just talked about an instant ago. So this is what Lambert described with this formula. You have intensity, which is basically, so the brightness that you get on the on one end is caused by the intensity of the light that you start with, the cosine of the angle, and the property of the material, the albedo. And you multiply all that together, and you get the result. The shader coders know that when they put their sphere, during the shader showdown, like usually they go with the Lambert because it's super simple equation and it gives immediately like relatable results. But we have a bit of a problem here because this part over here, it says how much light reaches the surface. So it has nothing to do with the material itself. And that means it has nothing to do with the BRDF. So I hope when I say it like that, I really make it like obvious and dumb. And it was not obvious to me at the beginning. Like when I started discovering this stuff, I had trouble like figuring what was part of the BRDF and what was not. And then I realized, oh, okay, like this is the difference. Like this is happening outside of the material, has nothing to do with the BRDF. The BRDF tells you what happens inside the material.
So for me, it just has clicked that like this part is in every BRDF for diffuse lighting, right?
In every BRDF. Period.
Okay, so like, yeah, right. But it's like, yeah. It's
well, not in BRDF, but when you write your shader and you have to put your equation, like this is going to happen, like this L cosine theta is going to appear every single time because it's
the light that goes into the material.
Yes.
It's not like the light we receive back. And I just learned that and made click, and a lot of stuff is now more clear.
Yeah, well then I'm happy because that's exactly what I was trying to do. Because yeah, for me too, like when I was doing shaders and then I was like, oh, the where is this cosine thing going? And then I realized a little bit of an interruption. Yeah. So when you say like you click, like it's for me the same thing. Like at some point the penny dropped, and you're like, oh, this is not the BRDF. And it's super important to have like a clear mental picture of that difference, to understand like where each, when you write lighting code, it can get pretty quickly involved, and I think it's important to understand which element belong to what and where they're coming from, especially when you're trying, to understand what you're doing and trying to debug if something looks wrong. Yeah, so oh, I was supposed to do some animations. Yeah, anyway. So the part that remains is the constant rho, which we can refer to the diffuse as a diffuse color. I've seen plenty of wording. There is the diffuse color, the albedo, the base color. If you have a metal rough pipeline, that it's all referring to the same thing. I think albedo comes from the astronomy world, where they say, oh, like this body over there is bright, like this planet is bright, and they call that the albedo, and I think that's where it's coming from. Anyway, we saw that the BRDF has two directions. There is a light direction and there is a viewer direction. So omega I and omega O. But in the case of the Lambert diffuse, that's a constant. So those variables, they don't change anything. Like that's the definition of the function. Like f equals rho divided by pi. The 1 over pi factor here is has to do with the integration because in the earlier equation I didn't put it because it was like, okay, we have this cosine and then we have some factor, but then if you have a BRDF, you have to remember that the BRDF has to be integrated over a hemisphere. Like you have a surface, you have light that potentially comes from everywhere. So in order not to have like problems with the amount of energy you get, because you put energy, say we saw the thing with one light. Now imagine you have like a gazillion lights all around the point that you're going to light up. So you put like a 360 light source and then you light it up. The light that's supposed to come out of it is supposed to be equal to the light that came in. So you just do an integration over a hemisphere, you find this 1 over pi factor. Not going to show it, but that's where it's coming from. Sometimes in the definitions, hello, come and have a seat. Not forcing you though. Sometimes when you see people talk about Lambert, or when you see a sample code or whatever, the pi factor is not there. Sometimes it's not there because it's canceled out with another pi factor somewhere. Sometimes it's because it's factored out, like they do all the computation and they know that there is 1 over pi that's going to arrive, so they put that at the end. And sometimes it's just a mistake, or I think some people, what they do is they consider, oh, well, I'm going to integrate that in the lighting, like multiply my lights by pi or something like that. But the difficult part here is make sure it's accounted for, because if you don't, then you're going to have like a light energy problems. But there is a solution to that. Now let's look at what our BRDF looks like in context. So we have the function, the Lambert diffuse, like just a constant. And we multiply that by the light intensity coming from the direction omega I. And then we have our little cosine law that we saw earlier, but which I'm just writing here differently. And with that, we're back to the equation that I wrote earlier. So same thing, just like different notation. That gives us the light intensity for one source of light, one direction light. But then the thing here, the f function. So maybe it's not going to be visible on the stream, but the f function, like you can replace it with anything. It doesn't have to be Lambert. You can put something else. So back to what we were saying earlier, like this is just the f function, and the L cosine is at the outside. And now if we apply that over the entire hemisphere, we get brightness from like all the lights all over the hemisphere. So basically the entire environment around the point. And this is, well, maybe a little bit simplified, but that's what we call the rendering equation. And that tells us for 1 point, so 1 point, I don't know, on the table, for example, how much light we see coming from out of that point when we take all the environment around it. So when you first see that, like this equation looks like confusing, and you're like, what is this stuff? But in the end, it's really quite a simple concept when you understand what like the different parts are. But the difficult part is to evaluate that guy, because this integral can really get like out of hands. So like basically solving that thing is what the graphics computer graphics community has been trying to do for decades. That's basically it. Now diffusion from microfacets. So what I mean by that, we talked about how when we have like the reflection, the specular light, it depends on how the geometry looks like at scale. So the Lambert model that we saw, it's basically making the hypothesis. Well, when Lambert did that, he was just measuring stuff. But now that we have formalized that as a BRDF, we realized that the Lambert model is assuming that a given material is going to send light like in a, what's the word?
Uniform.
Yes, but that's not the word I was looking for. It's going to reflect light in a uniform way. And now if we try to imagine what's happening at a, at a microscopic scale, suppose we have a material that has the property of, reflecting in a uniform way in all directions. The problem is you have this geometry, and like this face is going to reflect uniformly in this direction. This other one is going to reflect uniformly in this direction. But then, like, some of those rays are going to be intercepted. And anyway, if you're somewhere, you don't see like the hemisphere being aligned with the face, but aligned with the small geometry at scale. So in a way, you have to imagine that maybe this ray is going to matter less than the other one. So at a microscopic scale, like there is no way the geometry is not going to change this uniformity. So the idea is, okay, the Lambert is assuming that a given material is uniform, but how do we do when we want to take the geometry into account? And is this question relevant at all? So one good example, and oh, by the way, this is where the talk is going to get a little bit in shambles, because like those were my most prepared slides. So from here, it's going to be a lot more casual. One example I like is the moon, because let me show you something. Maybe I should have shown you this before, but anyway. This is Lambert lighting. You've seen that before. Typical, well, we have a nice normal. Let's pretend it's not there. This is what Lambert lighting looks like, and I mean, it works. You have like a sense of volume and whatever. And then this is what the moon looks like, and it looks nothing like I just showed to you. Like, even if we don't take into account the craters and everything, it looks flat. It looks like a disk. So that's because it has like a geometric property that it's called, like, it is said not to be a Lambertian material. It doesn't behave like Lambert. So this is why it would matter. There are a couple of diffuse models that try to do that, try to not behave like Lambert. So I guess now I'm going to switch gears a little bit. How am I going to do that? Show you both the slides and okay. So one first model that tries to do that is the Oren-Nayar model, and people who know really well the Oren-Nayar model probably are going to say, "What are you talking about here? You're not making any sense." Because earlier I talked about microfacets, and Oren-Nayar model is not a microfacet model. This is something you might have seen when you look on talks about graphics and people who try to replace the Lambert diffuse by something more interesting. So Oren-Nayar is one potential model to do that, but the problem is the assumptions of the model are quite different. So first, I'm going to show to you how this looks like. So back at this guy over here. So this is part of our demo engine. It's what we use, what I use mostly to do shader experiments. So I have like a live editor. I can change the maybe I can. Let's see how I do that. Let me try something. Just quickly switching the. Going to put this back here. Going to this guy. Did I break this? Nope. Did I break anything? Still working?
Yes.
Nothing exploded? Awesome. Okay, so I'm doing this so I can have like my editor on the right here. So a little bit of context. I'm trying to, so my goal is to have like an improved shading model in our tools, and I try both to have something that that works in many cases, and to have like a sort of a sandbox where I can, you know, switch bricks and try different lighting models, and this is my tool to do that. So on the left here we have our tool, so we have different like modes. So this is like showing a shader in different ways. I'm going to go back to it, trying different kinds of materials. This is our mesh editor. So here's a little guy that you probably haven't noticed that was present in our one of our demo, like on the side of. So this is how we model those guys. And then we have this texture mode here. So here we have like a. I did a very quick demo texture here just to show to you, but like for example, I have stuff like that for say. So yeah, this is our fancy texture generator sandbox tool. But so right now I'm just talking about this guy. Up and back to the shader. So this is a representation I use to try my shaders. So the idea is, one thing that is super important when you implement a BRDF is that you want your lighting to work in all conditions. And for example, you might have, you know, a single point light, you might have a directional light, you might have environment lighting, you know, where you take a texture and you consider that as a source of light, which is really nice to have like those nice to have elements that look more integrated in the environment. But then you might have, you know, like typical rendering, or you might have ray tracing, or you might have ray matching. And ideally, you want to mix and match those things and put them together. But the thing is, if you do that, you want your model to behave the same in the different cases, otherwise something is going to look out of place. So this is my sandbox to make sure that this is where we are. So it's using the shadow that's on the right, and we have like some live live reload of the shader. So I'm going to put back the reflection here just so we see it better. Okay. So what we have here is on the first two rows are polygonal rendering. So the first row is actually deferred rendering. The second row is forward rendering. And the last two rows, I'm not even sure which is which, but one of them is ray tracing and the other one is ray matching. And the idea is to make sure that it all looks the same. And I also intentionally put a very low resolution for the triangles, just to have, you know, if there is any interpolation error, I want like to see pop out. Same thing for the ray matching. I think I've put like a pretty low number of steps, so to have those things. And finally, like the last row, it's something that I've seen explained in the Disney paper, which is really interesting. So there is this paper from 2012, and I'm going to try to show it to you. Maybe that's a little bit too large. What was the title of that thing? Who was the guy? Is it this guy? Yes, Burley, that's the guy. Let me see. So yeah, in 2012, they made this super important paper, which laid the groundwork for like everything we've been doing since. And so yeah, those are the representation that I've just showed to you. So the idea is they took a database of measured BRDF, the MERL database, which is actually offline now, and they wanted to try to use a model that represented well the features that the artist found interesting in those materials. And then the question was, okay, how do we evaluate the model that we come up with and compare it to the measured data? Because it's a how many dimensional thing, you know, you have like you have this function which is a black box that has an input, like an incoming vector, an outgoing vector. So those are three dimensions each. And then you have the properties of the material, like the thing explodes, you know, how do you visualize something that complex? And they found out that there is a representation that is quite a good representation of the BRDF in a simple way, which is, so those the little images, and they explain it, I think it's page 4 or something like that. Yes, okay, here they explain what happens. So this visualization says, on the vertical axis on the left, it's, so bottom left, you have the light, the normal, and the view vector that are all aligned. So you imagine like you're looking from top, you have the light behind you. Top left, you have the light and the view vector that are opposed. So you're looking at the surface like this, and you have the light in front of your face. Bottom right, you have the light and the view vector that are aligned and at a grazing angle. So you're looking again your surface like this, but the light is behind you. And the right one, I'm not even sure what it means. It's confusing. Like you have the height vector.
You're looking away from the light.
No, you're still in front of the light, but it's something that doesn't make a lot of sense. I'm not sure.
The view light left, so we're looking away from the light. I have no idea if it makes sense.
Oh no, okay. So in typical BRDF representation, it doesn't the vector doesn't say which direction the light is going and which direction the viewer is looking. It's the opposite. It's which direction the light is and the viewer is.
Okay.
So you see like the surface like that. You have a vector coming out to the light source, and you have a vector coming out to the viewer.
Okay.
So what this says is the light is pointed toward the viewer is pointed toward the light. Like you have this light spot in your face. Well, my question is what this edge vector on the side means. I haven't mentally got an understanding, but that doesn't prevent me from implementing it and getting this result. And then they explain what the kind of result you get. So you have like an image like this, and so at the left here you have like the specular highlight, because why? Because at the bottom you're looking at the thing and you have the light, so you're going to have the glare in your face. At the top left you have the light and you're in front of it, so you're going to have a glare again in your face. So all the left you're going to have like this bright thing, which is the reflection of the light. At the top, they have what they call the Fresnel peak. So as you look at the grazing angle, you're going to have more and more reflection. So that's what's happening here. Oh, I should have taken a photo of that. The reflection, we tend to attribute the reflections to stuff that is metallic or stuff that is like glass, but everything is reflective. Like if you take a brick, you know, like you take a brick, then brick, you can't see yourself in a brick, right? You wouldn't use a brick as a mirror. That's my takeaway. Thank you for coming to my talk. If you take a brick and you put a light behind it and you look at it this way, like really at a grazing angle, you're going to notice that the brick becomes white, because at a grazing angle, it's going to reflect everything, and all the materials, they do that. Even like the most, you know, you take a sheet of paper, black paper, you look it horizontally, and as you reach like grazing angle, it's going to reflect all the light. It becomes completely reflective. And that's what happens at the top here. They call that the Fresnel peak. And at the bottom right here, they call the grazing retroreflection, which is one thing that they were really interested in, and therefore that we are really interested in. So it's something that you wouldn't notice in everyday life. Sorry. And I'm going to try to show you an example to you, and it's going to be ridiculous how much time it's going to take to show to you. Look, it's there. But apparently it's something that's super important for the artist. Like it's one of those tiny things you can't really put your finger on it, but they're like, I want this. Anyway, so that's that's the manual for those little thing that we have here. And the idea is, so this visualization, we have a roughness, so like very smooth on the left, very rough on the right. And well, you have this little speck of light that gets more and more diffuse until you can't really tell it apart. And then we have this this representation over here. So I'll come back to this guy later. Now here is my little ball with some typical shading that you might have. So right now it's GGX plus Lambert. So GGX is the specular, but specular is something that we're not interested in right now. It's still, you can tell it's smooth over here, like it looks like fresh paint, and over here it's, well, it looks more like almost like, maybe not fur, but it looks more fuzzy, And most of the visual clues we have with respect to geometry comes from the reflection, but the diffuse is going to play a role. So I'm going to disable the specular. There we go. So now we are back at having only the Lambert, and you can't tell which part is rough and which part is smooth. Let's switch to Oren-Nayar. Up. So now there is a difference. So Oren-Nayar is, if I'm not saying anything stupid, is based on what they call a V-cavity model. So this is where this guy is going to be useful. So the model we talked about earlier, the microfacet model, it says, okay, we imagine that the thing is made of, like, this is the geometry is like this, and the idea is, okay, like, how many faces we have in this direction, how many faces we have in this direction, and then try to make like, based on statistics, we try to make the model out of it. And but this has a little bit of like some flaws. For example, what happens if you have something that looks, like that, with a lot of holes in it, and you're like, okay, we have this face, but is the statistical representation of how many facets are oriented in such a way, is it representative of those holes? And I don't have the answer to that, but it's a question to ask. The Oren-Nayar model does something different. It's a V-cavity, so it says, okay, we're going to suppose that the surface is made of, like, cavities like that, and then the question is, depending on sorry, I don't have the paper in mind right now, like we would have to read it, but basically it's the core question is the model they use to represent the microgeometry is different. So they use that, and they say, we suppose we're going to have those V's. Let's see how, like, let's derive the equation and see what happens. I've seen other papers that don't use V cavities, but use like holes like that, like a small spherical holes. They're like, we're going to assume that the surface is made of small bubbles, and they get something different from it. I don't remember the name of the paper I'm referring to, but it's like, you have different ways of assuming what's going to happen at a microscopic scale. I mean, it could be any shape, Anyway, so the Oren-Nayar model looks like this. So now we do have a difference between the smooth surface and the rough surface. To be fair, without the specular model, specular reflection, I'm unable to tell you which is which. We can see a difference, but I wouldn't be able to tell you which is which. However, what's interesting in the paper is they measure the, well, maybe I can just show you this illustration right away, because it's probably one of the illustrations that's going to come out of it. Yeah, first image. So they take like a picture of a pot of clay, I believe. Let's show this here. Oh, come on, show me the picture already. Yeah, so this is like a major image, and they say, well, this is what we obtain when we do a Lambert lighting, and it doesn't look the same. And hopefully the next image is going to be the right one. No, it's not. Come on. Yes. And then they have their model, and which they've derived from the assumptions they made from the geometry, and they get a result that they consider to be better, and arguably it's better. I mean, better is not the right word. It's closer to the model, to the picture they're trying to match. So that's one thing. Come on. One problem, however, is if you have a specular model that uses one assumption for the for what the microgeometry is, and you have a diffuse model that uses a different assumption, how do you put them together? Like, how do you feed, for example, the specular BRDF, the Cook-Torrance uses a roughness, but roughness is not something physical. It's just a simplification of, you know, in that model, how do you present stuff? So how do you feed that roughness into the RNAi model? Like, there is no conversion of it. So some people are trying to do that. I heard that the derivation to try to go from one to the other is super complex. So that's one problem. Like, you can't really, I mean, you could just put a RNAi in your model and you're going to get like something that looks a little bit better, but it's still going to be broken because the two models don't match. They're like, it's like you're representing two different materials. What else we have? Oh, and now I can't switch slides over here. Let me see. So I have to do this. Yeah, that's not very practical. Let's get out of. Can I just do this, or is it going to? Yes. Okay. So there is this guy. I'm calling it Earl Hammond diffuse. I don't know how the industry is referring to it. It's from a GDC talk from 2017. This one. And it's a super interesting talk. If you're interested in BRDF, go watch it. If you're not interested in BRDF, it's okay. But the guy explains all sorts of things. He explains what the 4 is coming from in the equation that we saw earlier. Like, he does, you know, does his some work, you know, trying to figure out how we get this equation that everybody is talking about, and finds where it's coming from. And he goes to say, okay, if I assume that my model, my material is a Lambert diffuse, but it has geometry, and I derive, like, oh, I do all the equations, what do I get in the end? And he does get a result. He does get a diffuse BRDF, and I've tried it. I mean, nothing complicated here because he gives a code. And this is how it looks. So apparently I have some bugs because you have like those highlights here, which is probably like something going to infinity at the edge. So I still have to clear that up. But other than that,
it glitters. It's beautiful. It looks good.
Yeah, I can pretend it's on purpose, and I can put a Wayfinder music on top of it with the guys dancing, and we're good. So over here, I can tell you which is rough and which is smooth, because if you look like that over here, so at the center it's close to being the same color, but if you look at the edge, at the rim, you see that this triangle here, it tends to go darker at the rim, while this one, maybe it's not visible. Let's go to the other side. Wait, I'm going to put more lights. More light. Hup, more light. So yeah, this is the part where look closely. I'm telling you, there's something different. So yeah, like I guess the one that goes darker, it's you can see it, but the this one, like it doesn't stay the same color. It actually becomes a little bit brighter and a little bit more saturated. It's actually difficult to tell on the. I've tried to put some color that actually work, but
it's visible in the recording. So.
Yeah, because you have the original view. Yeah,
also, we had some 50 minutes past now, so just so you have a time frame for yourself.
So you want to wrap it up?
Not from my side, so
okay.
Rough estimate how long you have already.
So we have 10 minutes left. Is that what it is? 5 minutes left?
I guess we can probably still 15 or so, not sure.
Okay. Yeah. So on my screen, I can see like this edge here is like a slightly bit more brighter, brighter and slightly bit more saturated. But on the screen here, it's difficult. So that's one thing, you see it and you're like, well, if you think this detail it doesn't matter, you can go with Lambert. But if you have an artist in your group that's like, I want this, well, there is this difference here, and it's going to matter with like the rougher the material, the more retro reflection we're going to have. Trying to go a little bit faster. So this one, it's sorry. The GDC 27 talk, like the guy took the equation, and wrote down, and that's how he obtained it. But then the Disney diffuse guys, that's not the way they went. Like they tried existing models and they were not happy, and in the end they went, well, we're going to make one up. And so the Disney diffuse, basically they just made it up to match the expectations from the artists and from the models they have. And that's pretty cool. The original model is not physically, well, first it's not physically based because they made it up, but what is experimentally based? Like they have like those measured data, and they made a model that tries to match measured data. So, but it's not derived from a model. However, it's not, one problem it has is it's not energy conservative. Like it actually throws out a little bit more energy than goes in, which was, they knew it, and they say explicitly in the paper that's not a problem to us, like they accepted that. But Sébastien Lagarde did some work on it when he was working on Frostbite, took their model, did the integration, found like the factor and divided the whole thing, and is like, so there is a variation of the Disney BRDF on the Lagarde publication where he gives the factor to normalize it. And I'm going to quickly show. So, okay, this is the, let's try to find a good view of the Earl model, well, maybe something like this. And I'm going to switch to the Disney one. Be careful, I'm going to save, and at some point it's going to change when the speckle disappear. Okay, there it is. And it looks super similar to the like, except for the highlights that are not supposed to be here. Like, let's put it back. They have more reflection. Like here, even on the screen, you can tell it. Like you can see it's brighter here, right? But it's still like really quite similar. Yes, yeah, here like you can see it becoming brighter. So that's the Disney BRDF, and it's pretty simple to implement. Like they give the formula in the paper, and it's not something big. It's not something that you would walk away from. But that's the one that's from the paper, which is like giving too much energy. If I put the one with the correction from Lagarde, looks like this. So that's the normalized one. Looks, I guess it looks a little bit closer to the Hammond one. Yeah, look at that, it's like super close. I guess that's it for the models that I wanted to show to you. And I mean, like, look at that. We don't have any specular lighting, but we have a sense of, you know, I want to touch it. Like, you have a little bit of that, you know.
Can you show the view quality?
Yeah, sure. Yeah, I should have done that. You're right.
Yeah, what I was thinking of is, can we actually import like a picture from the bottom row and use this as a BRDF input?
If I'm not mistaken, I think Patapom tried to do that. So Patapom is this like a crazy guy who is going to go on one topic and dig until he hits a rock bottom and be like, I'm done, and switch entirely topic and never come back to it. And in between he's going to publish it. So look at his blog, and he tried to do that, and apparently he was not too successful.
Okay, so because it looked attractive to me to use just measure data for a material and use that in my demo or graphics code, and I'm like, yeah, I need red plastic, so I just search for measure data for red plastic and use that. But I guess we need more data.
So you could use the actual measure data, but that's like huge data. It's not something that you would be able to use in real time. And yeah, Patapom tried, you know, to take those slices and be like, hey, can I use this slice? And apparently he didn't manage to get something that was working quite well.
Okay.
But yeah, okay, let's go back to our different diffuse. No, first I want to no, this one. So we have this, and we were saying, I want to touch it, and like put back Lambert, and it's boring. Like, it's boring. Now back to this. So this is Lambert, and it's flat, which makes sense because it's constant. Then we have the Hammond guy, and we have this here, the retroreflection that we were seeing at the rim. This is the Oren-Nayar, which looks really different. Like the peak stops at half, and I actually, like, when I implemented it, I found two opposing implementations on the internet. I mean, the paper says it gives you the formula, but it doesn't give you like a reference implementation. And when I implemented it, I found like two different implementations on the web. I'm not completely sure which is correct, but this is what I get. And half of what I found on the internet does that as well. But it's still like less interesting. Like you have this peak, but nothing happens here and here. So this is the Disney diffuse. So the one that they made up completely. And so basically they have what they want. Like they wanted this thing here, right here. They wanted, okay, we can't see, but a darker rim over here. They wanted this part over here. This is when we normalize it, so it doesn't look too different. It's a little bit darker, but that's about it. And yep, that's about it. So let's go back to this guy. I like this guy. And if we put back the specular, so the GGX. No, that's not the GGX. That's a blin. Sorry about that. Yes, that's what we get, and that's pretty close to the images from the paper, which was no, not this one. Yeah, this one. What else do I have in the few minutes? Yes, something I haven't looked up yet, but that I really like. So you're all familiar with this photo, and on Wikipedia there is this close-up on the reflection on the guy, and you see this highlight around the head. This is not an illusion. Like, this is not the camera going off. This is not your eye. This is not JPEG compression. This is an actual effect. And I did a very quick search yesterday while I was like, trying to put my slides together and trying to find some CC, Creative Commons picture. If you see videos from drones, from anything that flies, or if you do fly too, look at your own shadow, and you're going to see, same here, like you have a slight highlight around here, you have a slight highlight around here, and it's not an illusion. It's something called the what's the name of it again? The retro. Come on. Retro surge. The what's the word? Retro reflection surge. Let me check because it's still morning. My brain is still not functioning. Opposition surge. That's the name. And I've seen very few papers that, very few models that do that very well. So over here, I mean, even if you're like having a walk in the countryside, you're just walking by the side, look at your shadow on the grass, and you're going to notice that as well. And one reason is because when you see your shadow, you're at a point where the shadows of whatever is on the ground, you can't see it because you're aligned with the sun. And so you have this peak where you see the best part of it because you have like everything that's 100% lit, and you don't have the shadows of whatever is on the ground. So you have this peak of intensity. And the only model I've seen that does replicate this is the one with those like spheric holes. The other ones I don't really see it. So that's an effect I find interesting, and I'd like to see shaders do that at some point. And okay, one last thing before we close. There is this thing called the white furnace. If you look at recent shader papers, shading papers, sorry, they talk a lot about the energy conservation and the fact that a lot of models, they lose energy. And the reason why they lose energy is because, they consider we have like this microgeometry, and they say, well, maybe there is some light coming here, and they say, well, this part here is going to be in the shadow. And on the other hand, they say, well, maybe we have, I don't know, light coming here, but maybe the viewer is over here. So we don't have this because this is going to be occluded here. And they just, drop it off and say, well, this is lost forever. But the reality is different. The reality is, okay, like maybe this is occluded, but maybe also the light that comes here is going to bounce around here, and eventually it's going to come out of it. And same goes over here. So they try to fix that problem. And one thing that tells them that there is a problem is called the white furnace. So the white furnace is you take a ball that is 100% white, 100% reflective, and you put it inside what they call a furnace that is emitting pure white, 100% white light from all directions. And you imagine that you have your camera inside. You shouldn't be able to tell the sphere from like, it should be invisible basically, because everything is white and the sphere is white. And I mean, it's not because you're blind. Like maybe you imagine like 50%, say 50% light, so it's gray, and you still can't see the sphere. It took me a little bit of a while to accept the idea of that you shouldn't be able to see it, but just say if the thing reflects 100% of the light that's coming to it, you shouldn't be able to tell it apart. So this has become a test. That's the white furnace test. You put something in here, you say it's reflective 100%. If my BRDF model is correct, I shouldn't be able to see the ball. And if you look it up on the internet, well, maybe I can do like a very quick search to show what I'm talking about. Yeah, okay, you're going to see like this kind of picture coming out. So, oh, Patapam. I was talking about him a moment ago. So where is it? Oh, nice, Patapam. Where is the picture? Where is it? Where is it? So yeah, that's the kind of stuff that he does with the... Yes, okay. So this is the kind of picture you get. So ideally, you want the row on the middle where you can't see a thing. By the way, there is a bit of clipping, like my picture on the screen and what they're going to see on the stream is a little bit different. But anyway, on the middle row you can't see a thing, and on the top row you have this coming out, which is telling you that there is some energy loss. And this is quite advanced stuff, but I think the white furnace is a good tool even if you're not going to do those things. You know, when I talked earlier about like integration, it's very easy to make a mistake in your integration. And I like to say that nothing looks like a correct BRDF more than a broken BRDF. Like if your equation is broken, you still have something on screen, it still looks 3D, so you're still like, looks correct to me, right? The white furnace is a really good test for that. Like what I do usually is you have the integration part. So I use the Lambert. Lambert is super simple. You just have constant. You reflect 100%. Put your thing in a white furnace. You make sure that it's that you don't see anything. So that's one case where in graphics where you want not to see anything. And when you don't see anything, you know that your integration is correct. And then you replace your Lambert with another model, and then you see if your model is correctly implemented or not. And that's my closing word, I guess, because we're over time already. You didn't have enough questions.
Yeah, thank you.
Do we have any question, and do we have any time for questions?
I guess does anyone have questions?
I mean, the time is not a problem. We can always close the recording, and okay. Sorry for the stream.
I would have one.
Yes.
When it comes to NFP, what is the axis of the last row of not this one, the wrong where this one, yeah.
Yeah.
Axis representation of
okay, let's go back to the to this guy. Yeah. So the axis is actually theta d and theta h, which is the angle between two vectors in the BRDF. But those vectors, they don't really represent something physical, you know.
You cannot relate it to physics.
That's what they try to do with the representation here. Let's see if the definition is somewhere. Where is it explained? Where is it? Oh, it's no. Wait.
Isn't H just the half vector between the two?
Yes, but the theta that they use. Sorry, I don't know in the paper where it's shown. I'm going to search for it, but so basically, like you have a bunch of vectors in your BRDF. You know, like you have the view vector, you have the edge vector, you have the light vector, you have the normal, and theta h, I don't remember between which and which, but basically it's you have those two. There are distances between two of those vectors, and here they try to explain what it means. So this vertical axis here is pretty straightforward. So the edge vector is perpendicular to the surface. So the edge vector, it doesn't mean anything. The edge vector is the vector of the it's the normal of the face that should be perfectly aligned. So so it's a mirror, you know.
So you could say that then it becomes totally white.
Sorry.
If this is like 0 and this is like then it becomes white.
So
the image on the right and the left upper corner is white.
Mm-hmm.
So this explains what you said.
Yep. Yeah, like the so a quick reminder. So the edge vector is, we're saying if the face, if the microfacet is going to reflect light, then it means it's aligned just like a mirror between me and the light. So that's the edge vector. Here it says the edge vector is perpendicular to the surface. So basically it's saying that the microfacet is aligned with the flat surface. And at the bottom, you have the light and the viewer that are aligned. So I'm looking at my mirror, the light is aligned with me, and I have the glare in my face. And as we move to the top, so the edge vector is still aligned with the normal vector, but I'm at the grazing angle. So I'm here looking at the grazing angle, and the light is in front of me, and I have the glare in my face. So that's this vector. This here says, I think it says what the angle is between h and the surface. So on the left here, the edge vector is aligned with the normal, but here it says the edge vector is at a grazing angle. So that means at the bottom, bottom left, again, I'm looking at my mirror and I have the light behind my head and I have a glare. At the bottom right, I still have the light behind me, but now the surface is here, so I don't have a glare at all. Have a good party, everyone.